Good morning, everyone. Sorry to drag you out on a Sunday, but I think you will be having another wonderful day here today at RISC. I hope you have had one yesterday also, and among all the poster sessions and the student talks and the keynotes. So today we'll be starting our day with a keynote talk from Dr. Alpan Rawal. He's a chief ML scientist at Wadhwani AI. He's by training, he's a theoretical physicist, which came out as a bit of surprise to me when I was looking at his profile. He has worked on early universe cosmology and black holes. That's a mix that we don't usually get in CS. He has taught applied mathematics and computational biology at Claremont Colleges in California, and later worked on research and AI teams at DE Shaw Research, Amazon, and LinkedIn. Today he'll be joining us to talk about ML in the wild and in the real world. I mean, we have all worked on toy ML problems like maybe house prices and stuff like that, where you have very nice acting data. But today he'll be showing us the other side of the ML algorithms, where we have to deal with real world data, where we have to deal with all the challenges of the data. I'd like to welcome him to the stage now.
This won't work? Okay. Thank you so much for that very kind introduction. Thank you, Varsha and Preeti, for inviting me for RISC. And thanks to all of you for coming here on a Sunday morning. I'm quite surprised to see the size of this audience, given that it's Sunday morning. I think when I was an undergrad, I don't know if I would have gone to a talk at 9 a.m. on Sunday morning. So it's very nice to see all of you coming here for this, and I hope this talk proves to be worth it. Right? So I'm going to talk about, the title is deliberately a bit provocative. I'm going to talk about machine learning in the real world, as mentioned, as opposed to machine learning in the research world. And I'm not making any value judgments here. I'm just trying to show you how different things are in the real world. So before I get to the meat of my talk, just a little blurb on who we are. You may not know about us. So I come from Wadhwani AI. We are based in Delhi, but we have a small office not too far from the IIT campus. We are an independent, non-profit, interdisciplinary, cross-domain AI impact institute. So we want to create impact through AI, devoted to developing and deploying AI-based solutions to create impact at scale by improving lives and livelihoods in underserved communities across the global south. So it's quite a mouthful, but it's actually very specific. We only work on problems that impact underserved communities only in the global south. That's the third world, formerly called the third world. Global south is the more politically correct term. And we work on problems that save lives, meaning health and so on, as well as improve livelihoods, education, agriculture, and so on. So that's just a little bit about us. And now we'll get back to the title of this talk. What do I mean by the real world? So there's, as far as we are concerned in this room, many of us have interest in AI or work in AI, and that's why we are here. There's two possible definitions of the real world. One is it's the world most of us live in, and by us I really mean the larger world outside, not us in this room. And the second definition is it's the world, the real world is the environment in which technology, namely a ML model, will be used, right? Now, when ML models are largely deployed on the internet, as is the case today, A and B do not coincide. Many of us who live in this real world are not exposed to the internet as those of us in this room are, right? And this is especially true in the global south. So what we do is we try to work for real world A. And so what we do is we build AI for social impact. So in countries like India, and we all know this, real world A is not the world of IIT Bombay, it's not the world of the office in which I sit. It's a world in which farmers commit suicide, because their farms are devastated by pest attacks. It's a world in which people die of TB, a disease that has been curable for the last 100 years. That's some kind of record. It's curable for last 100 years, and yet people, not just a few people, millions die every year. Right? It's the world in which babies are not receiving adequate nutrition in a country that has a food surplus. Right? And school-going children are not able to read. Right? So this is the world that we want to address through the problems that we solve. So what are the characteristics of this world? Well, it's messy, it's dynamic, it's constantly changing. It's impoverished and yet rich with data, with diversity of opinions, with diversity of problems, and so on. The data aspects are typically different from the type of data that you get from working on problems, on internet problems. You typically deal with small data sets. You typically don't have the big data problem. They're incomplete data sets, they're error prone, and the data is often available in spurts. So the data is definitely not high velocity data. There's annotation issues. Annotation is poor. It's very difficult sometimes to get very accurate annotation labeling related to that. Evaluation of any model that you build is very, very difficult in this type of real world context. There's deployment and adoption aspects. You can integrate your model into a software platform, but that doesn't mean it's going to be used. Right? So the deployment platforms are themselves basic or non-existent. There's internet connectivity issues. There's a need for user interfaces to your ML model that incorporate cultural contexts. And I'll be talking about all of these in the context of specific case studies. And there's a need for committed partners that can make sure that the work that you've done in building an AI model is actually used. So you need partners for rollout, adoption, and scaling. And our assumption in doing all this is that technology can make a difference to lives and livelihoods. And as we work, we are about a 5-year-old institute. And as we roll out our projects, we find more and more evidence that this is in fact true. So what can we do with AI in this type of real world? Well, as we know, modern societal problems across the developing world are very complex, they're dynamic, and they're all connected to each other. And this is a classic platform for the use of a technology like AI. You want to discover unknown or so far unknown correlations, you want to discover patterns, so that when you solve one problem, maybe you're solving other problems as well. So in pretty much any area that you can think of that impacts lives and livelihoods, AI can be used. In public health, you can use AI to screen for, to diagnose diseases, to recommend treatments, to drive health-seeking behavior among patients, to carry out disease surveillance at a population level, disseminate information better, obviously because of LLMs and so on. In agri and climate change, again, detecting pests, monitoring crop disease through satellite images or through images taken with basic smartphones, driving better agricultural practices, predicting crop yield in the future so that you can take the necessary interventions in advance. Again, disseminating agricultural advisories, information about weather, soil conditions, and so on. And monitoring the effects of climate change using satellite data, things like that. Right? In education, you can drive student behavior through the use of ML models, improve learning outcomes, and create better content. And I'm sure the list goes on in all of these cases. So the thesis behind AI for social impact, and I sort of make a distinction between AI for social impact and AI for social good. AI for social good is a term that's, I think, been hijacked by the West to mean removing the negative effects of AI, like biases and so on. AI for social impact I view as a more positive term, where you can actually use AI to do good, and you're not just addressing the negative effects of AI, right? So the thesis of AI for social impact is really to improve life and economic conditions for the underserved as a first priority. More important than addressing, although it's important to address biases and things like that, we consider this part to be more important than that. So this actually fits in very well with the UN's Sustainable Development Goals. For those of you who are not aware, these are goals that were adopted by UN member states in 2015. And the aim was to reach these goals by 2030. We are nowhere near reaching these goals. And COVID is partly responsible, but there are other issues as well. There's wars, there's political issues. And the goals can be divided into 3 broad categories: goals that affect society, goals that affect the economy, and goals that affect the environment. And you can see, I mean, the statements are fairly simple, but there's quantitative aspects to each of these statements. The statements are things like no poverty, zero hunger, and so on. And the aim was, at least the aim in 2015, was to achieve these things by 2030 across the world. And I don't think, we are close to achieving them across the world for any of these goals, right? So there's been very limited progress. Most of the Sustainable Development Goals are not on track to be reached by 2030. And in fact, developing country targets are much more far off than Western targets. And these are some examples. COVID-19 and Ukraine crisis have derailed progress on extreme poverty. In 2020, the share of population living in extreme poverty actually rose for the first time in 2 decades, and so on. There's still, food issues, there's disease issues. Progress against TB, malaria, HIV was slow to begin with, and it's been further derailed by the pandemic. 10 million TB cases worldwide, 30% of them are from India alone, and 33% of the world's TB deaths are from India alone. And this has been worsening. I think 2023 numbers were slightly better than 2022, but it's still pretty bad. There's been some studies, and I think these studies need to be repeated. There's a set of fairly old studies that show how AI can impact the Sustainable Development Goals. So there's a 5-year-old study from McKinsey that actually mapped many of these SDGs to specific AI methodologies that you can use to maybe address the SDGs. There was a separate study in Nature Communications in 2020, 3 years ago, which actually weighed the positive effects of AI on the SDGs versus the negative effects. The negative effects include things like bias and environmental issues because of training large models. And the conclusion was that the positive effects far outweigh the negative effects. And so this is sort of a worthwhile area to work in. So we'll get back now to this issue of real-world ML versus research ML. And this is a sort of very simplified representation of research ML. Please don't shoot me down if you disagree. I know there are lots of exceptions to this, but I'm giving you sort of a cartoon representation of what research ML is. So you start typically, you'd start typically with a fixed data set, what I call a God-given data set, or GGD. You extract labels and features. You carry out some algorithmic experimentation on this data set. You come up with a model. There's a subset of GGD that's usually reserved for evaluation, which we call the test set, and which I'm calling GGD prime. And you predict labels on this subset. You keep iterating until you can beat state of the art based on some God-given metric that's universally accepted, which I call GGM, and then you publish a paper. Right. Now, I know not all research ML is like this. There's lots of exceptions. But the idea is that you build models that you can eventually publish, and models that actually outperform others based on some standards that are accepted in the community, right? And based on data sets that are accepted in the community. So the standards are what I refer to as God-given metrics, and the data sets are what I refer to as God-given data sets, right? Now, how does real-world ML work by contrast? So first of all, it's not the blind application of research ML to the real world, right? There's a lot of misconception, especially among academics, that all you do is take a paper and apply it to a real-world data set. It's not just that. It's the application of natural intelligence, not AI, but our own intelligence, to select aspects of research ML that may be relevant to the real world setting, tweaking it appropriately, and much more than that. There's a lot of data and other issues that I'll talk about the rest of this talk. And it really starts with a respect for and an understanding of the deployment environment. So you can even you can almost think of the environment in which the model will be deployed as the God-given environment. It's the environment that's fixed, right? And you have to work backwards from the environment. So you work backwards from the deployment environment to define the ML problem. Often the problem is not well defined to begin with. The relevant metrics, and these metrics you may iterate on, the business metrics, the ML metrics, and you have to make sure these two sets of metrics are well aligned so that when you optimize an ML metric, you're actually also optimizing a business metric. And what are the data needs, and how do you need to annotate the data, and what other metadata you may need to collect, and so on, right? And so you're really iterating in this space of model, data, problem definition, metrics. All of these are dynamic and keep changing in a real world situation. So this is sort of a cartoon representing real world ML. You have the raw deployment environment in which you will deploy your model. You may design some nice user interfaces to this environment to make it cleaner. That's this box here. And then you may have some raw available data to begin with. That data set may be of size 0. You may not have any data at all. So you will have to supplement it with additional collected data. And this is again an iterative process. You may also collect some metadata along with that. Then you will have to sample this data. You will have to clean it, transform it in various ways, annotate it. And transformation includes sort of imputation and things like that. You will have to annotate it, and usually annotation is itself an extremely tedious process. This part is also iterative. And then you train your ML model, you do algorithmic experimentation here, train and validate it, deploy this model in your clean environment. And then of course you have your new data coming in along with any new metadata, and you predict a label, right? Now, all of the aspects in green are under your control, are things that you need to choose or you can pretty much define. The only thing that's given to you is a deployment environment and maybe some data to begin with. And of course, you have a loose problem statement. Problem statement is usually quite vague and loose. Now, when you do this, you also have to ensure that you don't get any type of drift, data drift, concept drift, and so on between your training data and the data that's actually coming in during deployment, right? And you have to constantly monitor for this. And then finally, once you have a predicted label, you have to do some type of continuous evaluation. And the final result of this process is impact. It's not a publication, right? So this is how the real-world ML cycle works. And as you can see, it's somewhat different and in many ways much more complex than a research ML environment. The research ML problem, all the complexity is in the algorithmic work. Whereas in a real world situation, the complexity is much more spread out. And now there are various pitfalls, and I know most of you know about the pitfalls of deploying AI models. You read about it all the time. And there's some things that we do in order to try and address these pitfalls. First of all, we never ingest any personally identifiable information in our data set, so we make sure that that's deleted from the get-go. We make sure data collection happens with informed consent. We make sure before we deploy a model, you don't just evaluate summary performance on an entire population, but you actually evaluate performance on protected cohorts to make sure that there's no significant variations in performance across cohorts. If there are significant variations, you need to address them through debiasing techniques. This is very important, especially in health AI models, to have human in the loop. The AI should not be the final decision maker. It should always be the human, right? We almost implement conformal prediction as a given in almost all of the models that we work on, so that we have uncertainty and we have we have confidence measures in our predictions. When we use LLMs, you have to make sure there are guardrails, you implement RAG, you avoid hallucinations as much as possible. But this is something we are still struggling with to make sure LLMs can be used safely. When we deploy models, we start with a passive deployment. A passive deployment is one where the model is deployed, it's making inferences, but the inferences are actually not being used to drive any interventions on the ground. We're just logging inferences in order to evaluate. That's a passive deployment. Once we are past the passive deployment stage, we go into pilot or small-scale deployments and check for robustness in these pilots. Ideally, we'd like to have pilots in as diverse number of locations as possible so that we check the generalization abilities of the model and the robustness of the models. Ideally, we also want to do A/B testing, but that's not very easy to do in the kinds of situations that we work in. So as you can see, all of this work requires a very collaborative approach. We as a 200-person institute can't do all of this, so we have to collaborate with a number of partners. We have 40 plus partnerships with governments, non-profits, academia, including IIT Bombay, and the private sector. We are an official AI partner of these ministries, and we partner with a number of such organizations. And our team really consists of a mix of people. It's not just ML modelers. We have domain experts, so we have doctors, agricultural experts, and so on in our team. We, of course, have the ML folks. We have user research and design people, engineering, and M&E team that designs evaluation studies. So now I'm going to deep dive into one of our solutions. It's newborn anthropometry. That's the team that's working on it. I'm just giving the talk. So I'll start with the problem statement. So the problem statement really has to do with babies being born in rural areas. And it's well known that the first 28 days of life, which is called the neonatal period, is the most vulnerable time for a child's survival. Right? So the statistics, global statistics are 1/3 of all neonatal deaths occur in the first day of life. 1/3, right? Half within 3 days, 3/4 in the first week. Right? And these are really sobering statistics, right? And this is in 2024. Sorry, no, this is from 2020, but it hasn't changed much. So in India, under the National Rural Health Mission, home-based newborn care has been implemented since 2011 to reduce mortality rates in rural areas. So there are these ASHA workers, workers that are employed by the government. Usually they are housewives who go door to door and counsel mothers on how to treat their babies. And they also do some basic things like checking the health of the baby, weighing the baby, measuring the height of the baby, monitoring their growth, and things like that, right? Now, how do they, and this brings us to what the problem that we are interested in is, how do they weigh babies in a home setting? So this is how they weigh babies. They usually take a piece of cloth like an old sari or something, tie it to a spring balance, and create a sling, put the baby in the sling, and then read the weight of the spring balance. Now, this system is heavily prone to errors, as you can probably imagine. The spring balances are not well calibrated, so they have 0 errors. The ASHA worker eyeballs the weight of the baby on the spring balance. As the baby moves, there are lots of fluctuations. And lastly, there's no motivation to enter the true weight. So, for example, according to WHO standards, if the baby at any point in their first, I believe in their first 6 weeks, dips below 2.5 kg, then there's a number of interventions that need to be taken because that's a danger sign. Now, these interventions have to be taken by the ASHA workers themselves who are overworked, right? So the temptation is always to round up to 2.5. So if the baby is 2.2 kgs, the weight is entered in their register as 2.5. And so if you actually look at statistics of baby weights across India, there's a huge mode at 2.5. Right? It's completely artificial. And it's because the WHO cutoff is 2.5 for taking interventions. So this is a huge problem. And there's similar issues with length measurements and so on. But the main issue is with weight measurement. But it's very important to measure weight in a timely manner so that you in fact do take the right interventions if the baby has low weight. So there's lots of these issues that cause errors, as I mentioned already: supply, maintenance, and performance of spring balances. There's cultural taboos that don't allow these ASHA workers to touch newborns, right? So then there's this complicated thing that happens where the mother puts the baby in the sling and the ASHA worker is not allowed to touch, and so that causes errors in the weight, all kinds of issues like that, right? Low motivation, as I already mentioned, errors in manual entries, and then data tampering because these ASHA workers are overworked. So babies are not in fact accurately weighed on the ground in home settings. By contrast, they are actually very accurately weighed when they are born in a hospital setting. So 80% of babies in India are born in hospitals. And there they are weighed with digital weighing scales that have an error of 10 grams, right? So they're very accurately weighed there. The problem starts when they go home, right? So they're not, the weight is not being tracked properly. So what can we do with AI? So the idea is we wanted to make sure that we address the cultural taboos appropriately. So we wanted to make sure that the solution is touch-free, it's robust, doesn't need this complicated spring balance that you need to calibrate all the time, right? And it should be simple enough to use. And we knew that ASHA workers are being supplied by basic smartphones by the government. In fact, this is rolling out across India as we speak. So we said, well, why not try and take a short video of the baby at various angles so that we capture some sense of volume of the baby, and then use that to infer the weight of the baby. So this is how we started working on this problem 4 years ago, and we envisioned this to be, we wanted this to be accurate, real-time, tamper-proof, etc., right? So, so the way this works is that the ASHA worker takes a video in a circular arc like this around the baby with their smartphone, and in real time they get a weight number. And we call this digital taraju. Taraju is a weighing machine. And the workflow is very simple. It's just you capture a video, you capture some other data about the baby, like the birth weight if it's known, and so on. The model estimates anthropometry measurements, and the relevant databases are updated. So you can both get individualized information about the baby that's tamper-proof, it's logged in the backend, and you can get summary statistics because this is automatic digitization as well. That's the other problem with this process, is that the ASHA workers often write down these weights on registers, so there's a further digitization step, whereas in this case, the digitization is done automatically. So this is designed to work in home and community settings, not in a hospital setting, even though it works better in a hospital setting because of better lighting conditions and backgrounds and so on. But in hospital settings, you have digital weighing scales. It works on low-end smartphones. It doesn't need any high-end equipment like depth sensors or LiDAR and so on. It requires minimal setup. It does require a fixed reference object in the frame. So the common reference object used in computer vision problems is a checkerboard. So we started working on this problem assuming that there would be a checkerboard placed next to the baby. After about 2 years, I think, of working on it, we were told that it's not feasible for ASHA workers across the country to carry checkerboards with them. It's just not feasible. And our solution simply didn't work without a reference object like that. So then we tried to find out what is the feasible thing for them to carry, and we looked at what is in their bag, and it turns out that that simple 12-inch wooden ruler that we've all used is something that they carry around anyway, and we started using that as a reference object. And after a lot of modeling work, we could make the wooden ruler work equally well as a checkerboard, as a reference object. So we're now using a wooden ruler. Doesn't require physical contact, and the video is not stored on the phones of the frontline workers. There's an interesting story behind this, which is that when we created an initial version of this solution and we went into the field to show it to mothers, we expected them to be impressed, right? So we expected them to think, oh, this is really cool, you can tell the weight of my baby from a video. But instead the reaction was, obviously you can tell the weight of the baby from a video. My question is, where are you storing that video of my baby? Where does it go? So there was a huge privacy concern even among rural mothers. And part of it is still a problem for us because if we tried techniques where you can automatically blur the face of the baby before it goes as an input into the neural net, but then that throws off the weight estimation quite a bit, right, because of the size of the blur and so on. So we still can't do that. But what we do is delete the data as soon as the inference is done. So it turns out this system now performs, we've been working on this for about 4 years. It now performs better than conventional methods. Over 95% of babies have less than 10% relative error in weight. And weight is really the hardest thing to infer. The mean absolute error in weight is at 111 grams right now, versus with the spring balance method, the average error is about 183 grams. And of course, you get all the other benefits of automatic digitization and so on. The data collection for this has been extremely complicated. We worked with 3 institutions, Seva Rural in Gujarat, PGIMER in Chandigarh, and Nilofer Hospital in Telangana. And over a 4-year period, we've collected about 24,000 baby videos from about 12,000 babies. So it doesn't seem like a huge data set if you're used to sort of YouTube scale video data sets. But for this type of thing, it was a huge effort to get to this many baby videos. Our data collection is still ongoing. And we have trained staff provided with calibrated equipment to measure ground truth and so on. The data collectors visit children on days 3, 7, 14, 21, 28, and 42 after birth. This is the standard protocol for home-based newborn care. And they capture measurements on mobile phones and capture baby videos. And one of the caveats is the babies have to be unclothed. We are still working on methods where you can have clothes on the baby and it works equally well. But right now we do require the babies to be unclothed. The measurements that we capture for ground truthing are the length, weight, this is the wrist circumference, the MUAC, head circumference, chest circumference. We also ask for, this data is actually typically noisy, but we log it anyway. The gestational age, the actual age, the gender, and the birth weight if known, right? Because most babies are actually weighed in a hospital, so birth weight is usually known. There's a short video that I'd like to show. It's about a minute long. Do we have audio? It's okay. Audio is not critical. It's just music. So. Can we decrease the volume a bit so I can talk? So this video actually shows a white background, but the model actually doesn't require a white background. It can be arbitrary. We've tested it under various backgrounds and lighting conditions. And then the worker takes a video, an arc around the baby with the ruler as a reference object. And this video actually shows an evaluation study. So the worker is also measuring ground truth using a digital weighing scale. And this solution, in fact, is fairly robust. We've trained on Gujarat data, evaluated on Punjab, trained on Punjab, evaluated on Gujarat, and so on. And it works quite robustly. So this is the model architecture. We have video input, CNN backbone. This is, for a long time we used a ResNet 50 backbone. We've also replaced this with clip embeddings, and the clip embeddings work slightly better than ResNet 50. We have a frame pooling method, and then the critical thing in this is to pose it as a multitask problem. So, and to combine with tabular information. The tabular information is the additional data that I showed, age, birth weight, and so on. The video combines representations from multiple this input combines representations from multiple frames of the video. And the multiple tasks here are the different anthropometric measurements, such as length, head circumference, chest circumference, and weight, obviously. So these are the corresponding 4 multitask heads. But in addition, we have 2 additional tasks that are actually not required at inference time, but which improve the performance of the model. And those are sort of baby segmentation tasks on the video, which is implemented through a fully convolutional network head, and a task where key points on the baby's body are predicted, certain key points. And so we had to do additional annotation for these 2 tasks as well. So when you set it up as a multitask problem like that, it actually improves performance on all of the individual tasks. So we had to do some pseudo labeling here for these 2 tasks, the segmentation task and the key point prediction task. And we actually did labeling here using models. So the annotation for the segmentation mask and the key points are carried out via fine-tuned models. So we did some annotation and fine-tuned the point rend and HRNet models to automatically annotate. And then use that as ground truth for the larger model. So the segmentation head, as I already mentioned this, has a standard fully convolutional net architecture, and the key point head has a 2-layer multi-layer perceptron architecture. This is what the data looks like. We had to make sure that we got representative data from all weight groups. So this is binned by weight, and you can see this is across weight. Training set, the training set is in red, test set is in blue. And this is sort of the gender distribution of the data. Evaluation metrics are fairly straightforward. We evaluate using the mean absolute error in the weight or the mean absolute percentage error. And I don't need to tell this audience what that means. So this is the summary of our results. This is on a training data set of roughly 10,000 videos corresponding to 2,000 babies, and a test set of 1,300 videos corresponding to 150 babies. We get a mean error of 111 grams, which is actually really good for use in the field. This is entirely in a field setting with poor lighting conditions, with varied backgrounds and so on. Over 50% of the samples have error less than 100 gram. And the MAPE is about 4%, and so on. So all of these numbers look pretty good for deployment, and that's what we are now gearing up to do pilots. What we'd like to do eventually is things like this. So we want to be able to automatically plot these growth charts for each baby. And here you can see an example for a male low birth weight baby and a female normal birth weight baby. The blue is the ground truth growth chart, and the red is the predicted one from this model. And what we are gearing up for is an evaluation that's planned in Bihar. We haven't trained this model on any babies from Bihar, so we're really excited to see how well it does. The second problem I'd like to deep dive into, I hope I have enough time. Yeah. Yes. Sure. Yeah. We can pause for questions.
I mean, since you said about the real thing, right? So I feel in the real world, the percent that goes wrong
Yes.
Has a bigger impact than a number in a paper.
Yes.
So that's one of my questions. I have another one also. But so what happens? I mean, you are not, if it's the actual data, the real data, and you can't keep having the ground truth also for the actual data also, otherwise there's no point in doing the AI.
Right. That's right.
So what is happening? Like, what's the real impact of this 5 or 10% that's going wrong?
Yes, so we actually, I haven't shown, I don't have that slide here, but we analyzed where things are going wrong. And it turns out that our model accuracy is much higher among low birth weight babies. So it's going wrong more among normal birth weight babies and classifying them.
Precisely, I was going to ask that.
So the errors tend to be more normal birth weight babies being classified as low birth weight, which is a more acceptable error than the other one.
But again, the whole real worldness. So,
yes.
Do you anyway do those conventional methods, because it seems, I don't know, would the magnitude of the error be, sometimes maybe the magnitude of the error from the AI could be just anything, whereas the spring thing, maybe the magnitude of the error is limited, or it can be bounded in some way because it's just a little bit off, and also the person who is taking the weight will probably have an intuition कि ये क्या 6 किलो का बच्चा 9 किलो दिखा रहा है, कुछ गलत है.
So we haven't done that's a good question. We haven't done a detailed analysis of the tail of the predicted distribution. We should probably look at that. But overall, we don't find huge deviations. We need to look at that in detail, but we don't find huge deviations. So we've got this tested in the field by various workers, and everybody is reporting back saying it's working well.
Okay.
They don't see these massive deviations, like you will have one case where the baby is 2 kg and it's predicting 5 kg or something like that. Okay. You don't see things like that. You don't see this.
The second question.
Now we do expect that if you take a model that's been trained, say, on Indian babies and take it to Africa or something like that, we do expect things like that to occur. So we are not very confident that it will work in a completely different demographic.
The second question is an end-to-end cost of this done? Because otherwise, is it really just better to get some rickshaws or something for the spring balance for them? Is that going to be cheaper than throwing AI at it?
So the spring balance, there's been a number of efforts by the Gates Foundation to make sure that babies are weighed accurately in the field. So they funded a number of what are called programmatic grants to make sure that spring balances are well calibrated, that they're available, and so on. And in fact, the Gates Foundation came to us with this problem and said nothing is working. So none of these methods are working. Now, of course, there's a huge development cost to this. We got a fairly large grant from the Gates Foundation to build this model over 4 years in the first place. Data collection is expensive. But we believe once it's robust enough, and the indications are there that you don't need to do too much additional data collection for it to be usable pan-India, then we think that the costs will be justified. It's a relevant question, but the answer is still somewhat up in the air. But we believe the costs will be justified.
Hello. How does the model perform with the obese children?
With obese children?
Yes.
I don't know how many obese children we have in our data set. We go to rural areas to collect data. There's hardly any obese children. And obese we are only collecting data from 0 to 42 days of age. I don't think we have any obese children in the data set. So I can't answer your question. I don't think the model will work very well on city children, who have good income and so on. I don't think it will, but because that's just not reflected in our training data.
Hi. Actually, I want to ask about the aftermath of this. You are doing such a great thing, your institute, but if we found out means each state elbow point where all the babies, healthy babies or risk-free babies are lie on that particular point, and we can calculate all those structured data and somehow predict that this should be done, then can it be possible by doing this that we just keep these all things aside, like weighing all these things, and just told the government that do this, and automatically all the things, those who are...
I'm not sure I understand. So are you saying that if you know regions where the problems are, can you just tell the government to intervene? Or is that what you're saying?
Yes.
Yeah, the problem is we don't know.
Finding out the elbow point of predicted babies of healthy babies.
What do you mean by the elbow point here? I'm sorry.
Means all the ranges of babies, those who are not at risk. by weight and height and all those ratios.
Yes.
Like
So
the
that is
model
known.
shows like that previous slide shows.
Yes. So the idea is that. So the idea is once you use this data, once you use this model to collect baby weights, then and the other anthropometric parameters, then you can aggregate all these numbers at a district level, at a village level, and so you know how well babies are doing in each of these districts, and the government can then take interventions, and you can automatically do this aggregation in the back end. Whereas with the current process, because there's no digitization happening, everything is written in these registers, and the ASHA workers are being told to use their smartphones to enter the data, but they're still used to using registers. Some of them use smartphones, some of them don't. So there's a whole digitization issue behind this, in addition to the accuracy issue. I don't know if that answers your question. Yeah.
So you said you are calculating volume and...
No, we are not calculating volume. So when we started doing this, we had a different modeling approach where we were trying to estimate a mesh around the baby and then compute the volume inside the mesh and then multiply by the density to get the weight. Because most babies, in fact, it turns out have similar densities, body density. The densities start varying after the first 6 weeks. The first 6 weeks actually. But it turned out that this direct regression approach where we directly regress on the weight turns out to work much better, at least within, we think that may be a data set issue, that because we still have a relatively small data set of videos, the direct regression approach works better. Whereas if we had a much larger data set, then estimating a 3D mesh might actually work better.
So if some neonatal baby has an abnormal bone density, so is your model robust to that, or is it error prone in that situation?
So if you had a mesh model, it would not be robust to that, because then the density would differ. This current model may also not be robust in the sense that it's only using visual information to estimate the weight. We're using some of the data, like we are using the birth weight as one of the predictors. So hopefully that abnormal bone density would be taken into account in the birth weight itself. But we have no way of measuring bone densities and checking this hypothesis.
So is your model generalizing to normal baby only, or it has outliers like abnormalities or other diseases?
No, so it generalizes. The main purpose of this model is to identify low birth weight babies. Right? So it generalizes well across the weight spectrum. But if you look at other types of abnormalities like missing limbs or things like that, we just don't have the data to test that. And collecting that type of data is going to be very, very difficult.
Okay.
And of course, incorporating that data into the training set is going to be even more difficult.
Yeah. Thank you.
Any more questions? Okay, I'll continue then. How much can I go over? Let me ask.
We started 5 minutes late? Yeah. Maybe 15 or 15. I mean 10:05.
Okay. Then I'll try to go through this quickly, and if there are questions, please come to me later. So this is, in contrast to the previous solution, this is in a different space. This is in the education space, and it's something that's already being used. It's deployed at scale, and it's being used. And the basic idea behind this is much simpler. It comes from the fact that only roughly 40% of grade 5 students in India can read at grade 2 level. So not even at grade 5 level, at grade 2 level. And this is in their own mother tongue. This is not English. So how can we fix this or try to fix this using technology, right? So we want to make sure that we have a way of automating and digitizing assessments. This is a problem. Just identifying where the problems are is a problem. Provide good reading recommendations to students in multiple languages, and make sure that this happens at low cost, doesn't require very high levels of literacy. We wanted to make sure that the technology can be deployed offline, doesn't require internet, and it can be verified by students. So what we've developed, and again I'll go through this a bit quickly in the interest of time, what we've developed is this solution called Vachans, which we call Vachan Samiksha, which is an oral reading fluency app. And the idea is quite simple. A student reads a piece of text, a given piece of text. This audio is pre-processed. We apply various speech recognition models to it, create transcripts from these speech recognition models. Each of them will create a different transcript. These transcripts are then aligned to the target text that needs to be read, and then combined to produce a consensus transcript. And then this consensus transcript is then compared to the target text to figure out what words the student got right, what words were substituted by a different word, what words were added, these are insertions, and what words were missed, these are deletions, right? And of course, these counts are functions of the student's reading ability as well as the accuracy of the ASR models. So these two things get mixed up, right? If the ASR student could be reading accurately, but the ASR model is not good, and therefore the final errors reported are really errors of the ASR model and not of the student, right? Conversely, ASR model could be really good. That's what we really want. We want the ASR models to be as good as possible within the scenario in which we are deploying them, and so that any errors that are measured here are the errors of the student. Right? So this is the challenge really. The challenge is it's not a standard ASR problem because of this challenge. So we do standard, I'm going to skip through a lot of this, I'm sorry. Please ask me questions later if you're interested. So we go through a lot of pre-processing steps on the audio, denoising, amplitude normalization, and so on. We looked at some open source ASR models. The one that we actually considered, we didn't want to develop our own ASR from scratch. So we looked at, this is AI for Bharat's wave to vec2 model. And the reason we like it is because you have frame level output for each audio, and it generates, so you can actually generate a timestamp for each character in the transcript. It doesn't have an encoder decoder architecture. So, and the other thing that we liked about it, there is no language model in the wave to vec2 model that will autocorrect a transcript. So for example, the Whisper ASR actually autocorrects a transcript, and that defeats our purpose because we don't want it to autocorrect. If the student makes mistakes, we want to catch that mistake, right? So we don't want a language model or some context in the background that will autocorrect a transcript. So for example, if a student, instead of saying happy birthday to my friend, says happy birthday to my friend, wave to vec2 actually captures it as happy birthday, whereas Whisper autocorrects it to happy birthday, right? Then that's what we don't want. So we used wave to vec2 as a base model, and then we did a lot of different types of fine tuning to this base model. And this is where the data aspects and the context of where this will be deployed come in, right? So we actually had a MOU with the Gujarat government. They were very interested in deploying it across the state of Gujarat, across all government schools in Gujarat. And so our data collection is mostly in Gujarati. We created a set of 300 grade appropriate paragraphs from 6 grades, grades 3 to 8, 50 paragraphs per grade that were appropriate to the reading level for that grade. And these paragraphs had been used earlier for oral reading fluency assessments by the Gujarat government. So they conform to their standards. And the way we did data collection and ground truthing for these, first we had teachers speak these paragraphs, and we assume that the teachers are mostly right. Okay, so we collected about 7,500 recordings from 33 teachers. And then we also had a lot of student data. We did an initial pilot where we collected a lot of student data, and we had about 2.8 million audio recordings of students, totaling about 90,000 hours. Right? So we had all this massive data set of audio recordings from students reading these paragraphs. Of course, these are error prone, right? Then what we did in terms of annotation is, we can't assume that all teachers will be perfect. So we applied the AI for Bharat model as a model to filter out teachers who are not reading well. So we said, well, let's filter out all recordings from teachers that have an accuracy by accuracy I mean the word error rate that's less than 60% as output by the wave-to-vector model, and then only annotated those that had accuracy higher than 60%, assuming that any errors there were errors of the ASR, not errors of the teachers, right? So the annotation for them was simply the target paragraph. You don't have to do any additional annotation. That because you assume they are right, the annotation of the audio is the target paragraph that they are supposed to read. For the remaining data, the student data, we selected a subset of this and did a very detailed annotation, including a timestamp annotation. But this we could only do for a very small subset, about 100 hours of data. We did very detailed time-step level, character level annotation. Right? So these are two sets of annotations that we did. We did a third type of pseudo labeling as well. Sorry. We had as I mentioned, we had 2.8 million audio recordings to begin with. We used a pseudo labeling strategy using models to do annotation, where we took a combination of the wave-to-vector model and a model that we had fine-tuned on the teacher data, right? And we said, well, let's align the model outputs with the target paragraph, and we created a pseudo labeling strategy where we say we only keep the hits and the insertions. That means we treat every substitution as correct. So we assume that any substitution error is going to be an error of the model. It's not an error of the student. And we do this only for students who have a score greater than a certain threshold. So this is a fairly complex pseudo labeling strategy that we arrived at after a lot of experiments. So we had a held out val set on which we evaluated word error rates, and that's how, and we iterated on this strategy to come up with that. So I'm going to skip this, sorry, in the interest of time, even though this pseudo labeling strategy is quite interesting. And so this is how we fine-tune our final model. We start with the AI for Bharat wave-to-vector model. We have the teacher data that's annotated, fine-tune on that. And this is full fine-tuning. We fine-tune all parameters to get to a version 1 model. Then we have the pseudo-labeled data. Again, do full model fine-tuning to get a second version of the model. And then we take only the small, very well annotated set of data, the small set of data, and we use fine-tuning using LoRa to get a final model. Okay, so this is how we did it. And again, why we used full fine-tuning here versus only LoRa fine-tuning here, it's just what worked best in our experiments. But our hypothesis is that because this is a small data set, LoRa fine-tuning seems to work better than full fine-tuning. But that seems to be the hypothesis. And then we had to compress this model to work in rural areas where there's no internet. So we carried out distillation using CTC loss on the teacher outputs. Again, I'm not going to go into the details. So we did distillation followed by another fine-tuning step on the data that we had. The data that we had was 15-second audio chunks. But then during inference time, we would have had to chunk the audio into 3-second intervals just to save on compute. So we did a further, what we call a streaming fine-tuning set on 3-second audio chunks, and that's how we come up with the final compressed model. So the compressed model the student model has 27 million parameters as opposed to the original model that had about 300 million parameters. And it fits well on a 1+ Nord CE2. There's only a 2% increase in character error rate between the original teacher model and the final student model. Details of distillation I'm going to skip. This is the way we evaluated the model. So we created 2 data sets. We had annotated data that was roughly 19,000 files, and we created 2 data sets. We created what we call an overlapping set, where the test set consisted of people reading the same paragraphs as those in the train set. So it's overlapping in that sense, but you have different people reading the same paragraph in train and test. Whereas in the non-overlapping set, both the people reading it and the paragraphs themselves were different. Okay, so that's the difference between these 2 sets. So here you have shared paragraphs across splits, and you have unique paragraphs across splits. And these are our results. So at various levels of fine tuning. So the AI for Bharat, and we have two data sets on which we evaluate. So there's our overlapping data set O, and then this is the Index Superb data set. That's a general ASR data set that Wave2Vec2 was evaluated on. And as expected, Wave2Vec2 works better than our model on the Index Superb data set. Our model works much better than any of these on our overlapping data set. But it's also good to see that our model, even on a general ASR benchmark, doesn't do too badly. So there's the fine tuning hasn't resulted in catastrophic forgetting. So this was good to see. And we find, we've done all kinds of ablations here. We find that the pseudo labeling significantly boosts performance, even on unseen paragraphs. I've already mentioned the compressed model. And the fact that the results are actually quite satisfactory even on the more generic data set Index Superb. This is a comparison of our model with commercial APIs on both the overlapping set as well as the non-overlapping set. And you can see that doing this type of fine-tuning and doing additional data collection was totally worth it. Our word error rates on the tasks that we want to deploy this for are much better than any of these other commercial APIs. So these are impact numbers. We launched in Gujarat in August 2023 as part of the G-Shala app. We've done 2.8 million assessments to date with this as of February. It's being used in 26,000 schools across 40 districts, over 1 lakh teachers, impacted 2.2 million students. And what we find is on average only 51% of words are spoken correctly. So we do have a long way to go to use this tool to improve reading performance. This is just a typical sort of teacher usage profile of the tool, and it maps very well to school start and school end. We have timestamps for all the usage. So what we want to do next, I'll be done in a minute.
We have a few minutes at least for questions because this is going to take a lot of questions.
Sure. So I'm just done. This is my last slide. So where we want to go with this really is we're collecting all this data from millions of students. We have their audio. We have the outputs of this, of the ORF that's actually, so we know what words are hard words at a location granularity across the state, right? So we can create a list of hard words at a school level, at a district level, and so on. We can do semantic matching to find words in the dictionary that are similar to those hard words. And using that expanded set of hard words, we can use LLMs to create new content at various difficulty levels. And then we can use that, have students read that content and lead them up the pedagogical ladder. So this is where we are going next. And I'll just end there. I think I'm way out of time. I was going to say something about our other projects, but I'll just leave the slide there. Happy to take questions.
So I suggest two questions and from somebody who has not been asking lots of questions. So anybody, let's just give a little bit opportunity. Please raise your hand. Anybody who has not? Okay, Preeti.
Yeah, thanks for the talk. I was wondering, the models that you have trained, how well, say, you would be able to use it to evaluate children, reading assessment of children in, say, schools in Maharashtra.
Yes.
So I think the choice of using the teachers' recordings insulates against, say, accent differences.
Yes, I was going to.
Which may not translate as well now if you move to a different setting, because.
Yes.
If you could just comment on that.
Yes, so it won't work out of the box. We need to collect additional data for Maharashtra. In fact, we're doing that already. And just the point you made about dialect agnostic. The teacher recordings from across the state make sure that this model is dialect agnostic. In fact, if you look at some of the other, there's Google Bolo and so on, which actually, if you speak in a different dialect, classifies that as being erroneous, whereas we wanted to make sure that speaking in a different dialect is actually correct, it's not wrong. So yeah, but for Maharashtra, we definitely need to do additional data collection and additional fine tuning.
One more question, or we can take it at
So I had a question upon it that that we are calculating the results of their data, like what are they speaking, how are they speaking. So can we also calculate like some form of errors in their speaking, like lisp and other things?
Yes, in principle, yes. So one of the things that we've been thinking about is, can you diagnose learning disabilities using the data we have? So we have timestamps on every, at a character level, right? So if you analyze the pause patterns, are there unnatural pause patterns between words, places where people don't normally pause? Can you diagnose something about the student? Of course, you need, additional ground truth to do that. And similarly with lisps and so on, we don't sort of classify the presence of lisps in the audio, but we could add that as an additional task. Again, it would require more annotation and so on using the data that we have.
Thank you.
All right, can we have another round of applause for Dr. Alpan? For this talk, I'd like to invite Preeti ma'am to give him a token of appreciation. Well, I'm sure we all have gathered something about how difficult it is to apply ML in the real world setup, especially when you don't have digitization readily available as we have in our campus or in offices. Next, we have Professor Maithili Vidguru from our department. She is an associate professor in our department. Her research work spans computer networking, operating systems, and network systems. She earned her BTech from IIT Madras and did her MS and PhD in computer science at MIT, 2006 and 2010 respectively. Today she'll be diving into Linux network stack. She'll be talking about how network packets are received and processed within the operating system before it is delivered to your application. She'll also be giving a lot of examples, so it's a nice. I'm excited for this. I want to understand how different network stacks and latest network stacks work. Over to you, Professor.
Okay, hello, good morning everyone. So in this talk I'm going to be talking a little bit under the hood of what happens inside the Linux kernel when we send and receive packets, right? So I'd like to thank my students Debojit and Preeti who are here for some of these slides. So how does this talk differ from in general the other stuff that we learn about networking, right? So normally a lot of you who would have taken some networking course would have seen what are called socket programs. For example, you know that most networking applications are, are built as client and server applications where the clients and servers have things like sockets that are listening at some IP addresses, port numbers, and you connect these sockets to each other, you can send and receive messages. So if you've taken a networking course before, some of this is familiar to you and you would have heard these terminologies, right? And a lot of web applications today, web servers, clients, email, gaming, all of these things are typically, there is some API like sockets, which is a C, C++ abstraction, or in other programming languages there could be different abstractions, but all of them point to the same thing, that there is some mechanism available into which you can send and receive messages, and a similar entity on the other side will receive these messages, right? So this is how networking applications typically communicate. So if you look at a networking course, you're going to learn a lot about, what happens when this networking data leaves the computer. You have layer 2 switching, you have IP routing protocols, and TCP, congestion control. All of that stuff is what you typically learn in a networking course, which is what happens once this data that an application gives leaves the host. But in this talk, what I'm going to try and talk about is what happens inside the end host itself when you send and receive data. So this content is something that falls in this weird boundary between a networking course and an operating systems course, and so sort of kind of gets left behind in most curricula. Whereas for modern system design, a lot of what happens here is very important when you look at real systems being built out there and where do the inefficiencies arise and so on, right. So in this talk, I'm going to try and demystify this part of it. When a networking application writes something or reads something from a socket, and what happens from that point till the point when the packet leaves the machine, at which point I think there's a lot of networking textbooks that talk about switching, routing and so on, right. So this is where I'll try and focus in this talk. Okay. So we'll start sort of the deep dive, we'll go step by step. So the first thing, of course, in any operating system, so these networking devices, your Ethernet device, your Wi-Fi adapter are all devices that connect to an operating system on a desktop or a laptop, and all of these devices are managed by device drivers. So device driver is a piece of code that manages an external device on a computer. Right. So for a networking card, also called an NIC or a network interface card, also there are some device drivers. Different devices have different device drivers. And the first step to sending and receiving data from a computer is actually a device driver talking to that hardware device and configuring it. Right. So these are the basic steps that happen. Every device driver talks to the NIC, the network interface card, through a process known as MMIO or memory mapped IO. What this means is that there are some registers or some places, some pieces of information in the device that your device driver accesses and configures them, saying this is how you have to send packets, this is how you have to receive packets and so on. So that is the first step that happens. And then from now on, so what we are going to do is we are only going to focus on the receive path here. What happens when you receive a packet on your computer, right? The packet has traversed the internet, has been routed, forwarded, TCP, blah, 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 all of that has happened and the packet has reached your computer. What are the steps that happen until it reaches your application? So we are going to focus on the RX path. The transmit path is somewhat similar and simpler. Okay, so first the device driver has configured the network card. They have established communication saying if you receive any packets, this is what you're supposed to do. So the next thing that happens is when the network card, your Ethernet card or a Wi-Fi card receives some data, receives a network packet, the next thing it will do is it will do something called a DMA or a direct memory access. What this means is it will go to some area of your DRAM, your main memory, which is under the control of the operating system. It will go to some location. How does it know what this location is? The device driver in its initial configuration has given it some information, right? It will use that information and it will go to some part of the OS memory and it will directly copy the packet into that OS memory, right? So this happens automatically without your operating system, anybody else getting involved. So this is called DMA or direct memory access. After which point the NIC raises what is called an interrupt. So any external device, your network card, disk, keyboard, mouse, anything, when it has an event occurs, you've typed a character on a keyboard, when any such thing happens, any external device does what is called raising an interrupt. This basically tells the operating system, hey look, some event has happened, you got to handle it. So this guy puts the packet into the OS memory and raises an interrupt. Right, so this is just basic interrupt handling that if you've taken a course in operating systems, you should know. So interrupts come from external devices, and whenever an interrupt comes, there will be usually, your CPU is running some user program that's, scheduled on the CPU, and that guy is continuing to run. And when an interrupt happens, that is when the operating system comes into play. This is called, it's also called a trap. So when this happens, your CPU's context, whatever is the context of this user program is, you know, the state of all the registers, everything that is saved, then the operating system comes into play. Now some external event has happened, right? The program that is running doesn't know how to deal with it. So the operating system comes into play, it runs this interrupt handler, takes care of that event, and then goes back to the user process again. So this is what happens for any interrupt. So is the case for interrupts from NICs whenever network packets arrive as well, right? So there's a lot of stuff going on here, right? So this is not an easy process. You have to kind of, you know, pause this program correctly so that it can resume again correctly. You have to switch from user mode to kernel mode. What does this mean? This means you're going into a more privileged mode where the operating system can do some privileged operations. So all of this is sort of like it takes some number of CPU cycles, and this is not cheap to do. So handling interrupts are very expensive. So why am I emphasizing this? We'll come to it later. So anyway, this is general interrupt handling. So also the similar case happens for networking devices as well. Whenever a network packet arrives, there is an interrupt. But a few differences, some small differences when it comes to network interrupt handling is that, so normally if it's just handling a keyboard interrupt, you typed a character on a keyboard, there's a keyboard interrupt, there's a little bit of work to be done, you know, you take that keyboard character, you copy it into memory, you're done. But for networking packets, there's a lot of work to be done when you handle an interrupt. You have to do layer 2 processing, layer 3 processing, IP routing, you have to do the checksum, and if you've studied TCP congestion control, there are these large algorithms that have to be run. Oh, is there a loss? Should I increase my congestion window, decrease my congestion? Like there's a lot of thinking to be done, right? So all of that, doing it during this time when, you know, this process has been interrupted and, you know, some other process is running, you've interrupted it, doing all of that during the interrupt handling is very cumbersome. Therefore, for network interrupt handling, what operating systems do is they split this interrupt handling into two parts, which are called the top half and the bottom half. So the bare minimum that you need to do to handle an interrupt, which is just acknowledge, tell the device that, hey, you know, I've listened to you and, you know, I'll take care of this. That is done in the top half. And then this top half basically schedules the second part of the interrupt handler called the bottom half interrupt handler, which does a bulk of all the TCP IP processing, because that takes a lot of time and you don't want to do it when you have interrupted an existing process. So later on, when the CPU is free, when no other process is running, that is when this bottom half interrupt handler gets scheduled, and this bottom half is the one that fully processes the packets. Right? So this is very unique to network interrupt handling, simply because it is a very heavy weight interrupt handling mechanism that is needed. So the other thing that what happens between the top half and bottom half is that the top half disables future interrupts. So once you have interrupted, you don't want the network card to be constantly ringing the doorbell and saying, hey, there's a packet, there's a packet, there's a packet. So the top half disables interrupts temporarily until the bottom half runs, and when the bottom half runs, it will handle all the packets that have come in. And once the bottom half runs, then it re-enables interrupts again. Right? So what happens during the top half is, you know, your NIC has done the DMA, has interrupted whichever process is running. It temporarily takes a pause, runs the top half interrupt handler and goes back. Okay? So at this point, I'd like to also introduce this terminology of the device driver and the NIC share what are called these TX and RX rings. What are these rings? These rings are nothing but pointers to received and transmitted packets. Now the NIC cannot just dump the packet somewhere in memory and go away, right? It has to tell the operating system where the packet is. So what it does is a pointer to this packet is stored in what is called this ring. Now this ring is a shared piece of memory that both the device driver and the NIC know where it is. So whenever the NIC puts a packet, it updates the pointer in this. The pointer is put in the RX ring, and whenever the OS runs later, it will look at the pointers of these packets from this RX ring and it processes them. Right? So this is, so far we have done with the running of the top half interrupt handler. So the next step is, now whenever this process that was running that did the top half interrupt handling, it gives up the CPU scheduler runs, there's nothing else to do. So at that point, when the CPU is idle, this bottom half interrupt handler gets scheduled. This is also called, this process is also called Ksoft IRQD in Linux, but it is basically a OS process that handles a bulk of the network processing, right. So, this bottom half runs asynchronously later, not when the packet is received, but when the CPU has free time. So, this bottom half runs, and then the bottom half once again makes, so there is this received packet, then you have to kind of now parse the packet, understand what is the layer 2 header, layer 3 header, what is the TCP IP headers, what is the information there. So, it creates another data structure called the socket buffer or skbuff. This is the name of that data structure in Linux. There is the skbuff that gets created, and this skbuff is basically has all the packet headers along with a pointer to the packet, right. So, all of this happens in the bottom half interrupt processing. And in the bottom half, as part of the bottom half itself, you also do the TCP IP processing. Now, check the head, checksums of all the headers, TCP, congestion control, sequence number, is it received correctly or not, should I, send an acknowledgement, what acknowledgement, all of that happens as part of the bottom half interrupt handling. By this time, note that you have the packet in memory and you have the skbuff that is pointing to the packet, and this skbuff is what gets passed along to all the TCP IP functions, right. By now, the packet is off, it has been plucked off the RX string, the device driver is no longer responsible for it. This packet is now traversing the packet along with a whole bunch of other pointers to headers. The skbuff has pointers to headers as well as pointer to the packet. This is the guy that is going through the network stack at this point. Okay. And finally, after all the processing happens, all the networking processing happens, the packet has to eventually reach a socket. Remember that at the beginning we said sockets are typically the most common API used to send and receive packets. So, an application has opened a socket, an application writes into a socket or reads from a socket. Now, when this packet has been received, the socket buffer, after doing all the TCP IP processing, you identify which socket it belongs to. You look at the port number, IP address, everything. You identify the socket that should receive this packet, and you go take this skbuff, tag it along to this socket. This socket also has a point, some place where it stores all the received data for that socket called the socket buffer. So, you take this skbuff, tag it along to this socket, right. So far the packet is in the OS memory with all of these skbuff or RX string was storing pointers to this packet, right. So, we have one copy of the packet in OS memory. Now, when the application reads from this socket, then this data, this network data, the payload, the information, the message that has been received on the socket is copied into user memory, right. The user has some array or something, some character array that it has asked to has given as part of argument to the read system call. So, when you read from a socket, now the OS and the user space, they do not share memory by default, right. So, because of security and isolation. So, the user space memory, there is some variable in the user space that is some array that is has to store this packet. Now, this packet is copied from the kernel memory to the user memory, right. So, at this point when you read from a socket, all of this story has happened, and the packet that has been processed fully by TCP, now that packet is copied into user memory, and now the networking application, if it is an HTTP GET request, the web server can read the request, send a response back, and so on, right. All of that happens at the user space of the application. Okay, I hope this is clear so far. So, as you can see, there are a lot of steps, and this is a very high overhead process. There are many inefficiencies when it comes to the Linux network stack. For example, you have frequent interrupts. Whenever a network packet comes, whichever process is running has to stop, has to save context, jump into kernel mode, go back. So, interrupt handling imposes a certain overhead, certain inefficiency in the system. Then the next thing you have is you have this frequent context switching between there are regular user processes running, then there is this kernel process, the soft IRQ, the bottom half interrupt handler that is doing all the network processing. So you have to constantly switch between your actual application and this kernel process, which again there is a context switching overhead involved across processes, right. So there is switching overhead between user space kernel mode, there is switching overhead across processes, and finally there is this packet copy overhead, right. The packet is first DMA'd into OS memory, and then the OS does all the processing, and then the packet is copied into user space. So you have multiple copies of the same data lying around. Now when Linux network stack was designed, I mean network cards had much lower throughput, and all of this didn't seem like it was such a big deal, right. But today what you have is you have hundreds of Gbps of networking hardware coming up, and you have the same operating system with the same architecture that was designed decades ago at much lower network speeds, the same guy running, the same network stack running with higher and higher networking speeds, right. So today, so this is from a recent paper, if you take a 100 Gbps network card and you run this run it on Linux and run a networking application on Linux that is simply reading packets, you can nowhere match the line rate, right. You are getting hundreds of Gbps of data even with multiple threads and multi-threading, parallelization, whatever you do, the throughput that you get, of course these numbers may vary and there is a lot of work on how do you make this number go higher. But the bottom line is you cannot just keep doing whatever you are doing before and expect to match the speed of networking hardwares. As 400 Gbps is also found in data centers today, and you cannot run the same operating system on top of these higher and higher networking speeds and hope to be able to process. So if you have a web server or any other application that needs to process 100 Gbps of data, it cannot run on Linux the way Linux is today, right. It has not been designed for those kind of speeds because there's a lot of overheads that we've just discussed, right. So today people are coming up with newer ideas, and while I cannot go into a lot of depth of those ideas, I'd like to give a high level flavor of what is it that people are looking at. Right. So on the left here you have the generic network stack where for every packet there is an interrupt, you process the packet, you copy the packet to user space and all of this. One alternative to this that the state of the art today is exploring is you are trying to offload some of this packet processing into the kernel itself, right. So this is called in-kernel offload. Now of course you can always write, you can hack the Linux kernel, change the source code, write kernel modules to process packets inside the kernel, but that is not something that everybody can do. So today people are coming up with techniques that makes it easy to offload some of this packet processing into the kernel itself so that you handle the packet here itself, at least most of the packets here itself, and don't do this copying into user space. So the application somehow communicates something to the kernel in an efficient manner, and the kernel handles the packet at this level itself so that you are avoiding all of these packet copies. So that is one way, pushing things into the operating system itself and avoid crossing this kernel user space boundary. The other technique is what is called kernel bypass, where you say forget it, I mean Linux, this architecture itself makes my head hurt, I am going to leave all of this aside, I am going to directly take packets away from the NIC directly into my user space application and bypass the operating system fully, right. So the next set of optimization techniques are called kernel bypass methods. Right. So we are going to briefly look at what these two are. Of course there are pros and cons, right. So as you can see, this one is likely to give you better performance because you are kind of getting rid of all of this clunk here and going directly to user space, but at the same time you are losing control of the operating system, whatever control the operating system had with respect to maybe you have existing scripts and tools and all of that don't work over here, they work better over here, right. So there is a trade-off. So first let's look at what are these in-kernel offload techniques. So the most common and popular one is what is called eBPF, or Extended Berkeley Packet Filter. I mean let's not worry about how this name came about, but what this means is that today in the Linux kernel you can actually write some programs called eBPF programs, which actually where you can write some packet processing, look at the packet, if this is the header, do this, do that. You can write packet processing code in in this framework called eBPF, which gets compiled and verified and then loaded into the kernel. So now this is not like hacking the Linux kernel to do packet processing. This is much more safer. You are guaranteed that this eBPF code will not crash the kernel, because there is a verifier step over here that ensures that the code you're writing is safe and it can be, you know, dynamically loaded into the kernel. So you can write these eBPF programs, and then these eBPF programs run at what are called hook points, right? There are specific places inside the kernel during the packet processing where the OS has, you know, given you a place to push this eBPF code, you know, when in the device driver, during the TCP/IP processing, when you are, you know, assigning packets to sockets. There are multiple hook points inside the kernel where you can write your own code, eBPF code, to customize the packet processing. So earlier everything had to go to the user space. Now everything does not have to go to the user space. A lot of the stuff you can handle within the kernel itself safely by doing custom packet processing in eBPF. Right? And there are things like eBPF maps. So there are ways. So an eBPF map is nothing but a shared, you know, key value store, a hash table kind of data structure where the user space can say, hey, for these kind of packets you do this, and the eBPF program will take instructions from the user space or give back information to the user space, exchange information, and you can actually do custom packet processing inside the kernel. Right? So this is one way, and there are several hook points, right? So I'll just talk about a couple of the hook points. One of them is what is called the XDP hook, which happens directly at the device driver. As soon as the device driver starts, you can actually run this XDP hook. So, you know, a lot of simple packet processing you can do here. Then there is something else called the TC hook that runs later on during the TCP/IP processing when you have parsed the TCP/IP headers. So here you have more information available to process the packet. Here you have less information, but this is faster. So there are different trade-offs. There are multiple ways in which you can, multiple hook points where you can run these programs. Now eBPF has many applications today. For example, things like firewalls, you know, you're getting a lot of extra traffic. Instead of this traffic going all the way to your user space program through these 20 different steps we've seen, you can just drop it at the device driver itself. You can look at the packet, you can do some custom packet processing, you can drop the packet. And, you know, things like observability, collecting statistics about applications, you can write such code in eBPF. And in fact, people are also offloading, if your application is doing some processing, a lot of the common case processing that can be done quickly can be offloaded into the kernel, into eBPF programs. So today there is a lot of interest in eBPF. It is being developed very actively as part of the Linux kernel, and there are many, many interesting applications that are being built on eBPF. Right? So maybe I'll take a couple more minutes. I'll quickly go through this kernel bypass method as well. So what this kernel bypass says is it's slightly different from eBPF. In eBPF, we were pushing custom logic into the OS. Here, what we are saying is let's just bypass the operating system, right? So you can write a program in the device driver that will basically take all the packets and directly copy them into the user space application, bypassing all the TCP/IP processing that happens inside the kernel. So there are special type of sockets. So normally you have TCP sockets, UDP sockets. You also have a type of sockets called AF-XDP sockets, which basically whatever packets that match a certain pattern at the XDP hook, which is the device driver hook, you can write an eBPF program that will just directly pass them on into your user space program. And if you have device driver support, you can actually tell the NIC to DMA the packet also into user space. Now there is no more packet copies. You don't have to copy the packet into OS, copy it to the user space application. You are completely bypassing the kernel. You are basically telling the device DMA the packet into the user space application, and whenever the packet comes, just give it to the user space application. You are completely taking the OS out of the loop. Right? So this is called AF-XDP. These are a special kind of sockets on which you can build applications. So all of these things, eBPF and XDP, they all work together, right? So when you get a packet at the XDP hook, you can do things like you can drop the packet, or you can forward it through the TCP/IP stack into regular applications, or you can take the packet, give it to this AF-XDP application that has bypassed the entire kernel stack, right? And this XDP and eBPF, they are also used to connect up containers. They work along with virtual devices that are used to connect up containers. So eBPF and XDP together, they actually form a very important part of the cloud networking stack, and this lets you run networking applications efficiently on the cloud at high performance. Right, and finally DPDK is also one more, it's slightly more widely used than AFXDP, which is somewhat newer. So DPDK, or Data Plane Development Kit, this was initially pioneered by Intel for their networking cards, but now support is widely available for all high speed networking cards. So what DPDK does is also similar to AFXDP, where you are completely bypassing the kernel. You put in some kind of a dummy device driver in the kernel that does not do much, and then your device driver is actually a user space device driver which directly talks to the NIC, gets the NIC to DMA packets into user space memory, and now in user space memory you have lot more control. For example, DPDK does things like huge pages which let you, avoid TLB misses and access memory much more efficiently, and it pre-allocates all these packet buffers so that you do not have too many pointer traversals when processing packets. So there are a lot of optimizations that DPDK does, but the basic thing it does is there is a pole mode driver, there is a user space device driver that disables any kernel processing, and periodically it will go to the NIC, get a batch of packets directly into user space and process them, right. So this basically eliminates all the inefficiencies of the Linux kernel stack. Now with all of these techniques today, networking applications can actually very easily get 100 Gbps on a small number of CPUs, with AFXDP with 6 threads, DPDK using 4 threads, with a small amount of CPU usage, you are actually able to sink in and process, digest hundreds of Gbps of data very easily, right. Without all of this, it is actually very challenging on the bare bones Linux network stack, but today with these techniques it is actually possible to build high performance networking applications very, very easily. So this is the summary of my talk. I've just to recap, I've basically told you how the traditional Linux network stack works, from the packet coming in, DMing into the kernel, packet processing, all the context switching, copying it into user space, the inefficiencies involved there, and the 2 optimizations that are used today. So given that you do not want to do this dance across user space, kernel space, crossing these boundaries, there are 2 ways. Either you push your packet processing into the kernel itself, there are ways to do that safely using eBPF, or you say you want to bypass the kernel fully, take your packet directly into user space and you deal with it in user space using frameworks like AFXDP or DPDK. And today the state of the art, if you are building any high performance networking application, so today the buzzword in the industry is what is called NFV, or network function virtualization. What this means is I am going to build whatever was built as software earlier is whatever was built as hardware earlier, a lot of that stuff like firewalls, load balancers and various gateways and routers are actually being built as software today instead of hardware, and this software needs to perform well, and it is using frameworks such as these that we are hoping to see high performance networking applications in software, which is driving the trend for NFV, right. So I think I'm out of time here, so I'll stop. I'll be happy. Do I have time for a couple of questions? Yeah. Okay. I think there are a couple student talks now, and then tea. 11 o'clock is the break.
Maybe just 2 questions.
Yeah, okay. If there are any quick questions, yes.
Ma'am, as you said, the packet processing actually performs in the kernel mode, and since kernel mode is a non-preemptive in nature, if any big packet processing program are there, will there be any starvation of other programs?
Yeah, so that is why it happens in a separate process, right? The bottom half, the K-soft IRQD process. So that is not non-preemptible.
Oh.
So which is why the non-preemptible interrupt handler is actually, the top half is actually very slim. Okay. And most of the processing happens in the bottom half, and then you could have starvation. For example, at high speed you may have this K-soft IRQ not getting enough cycles and not processing packets, right? Yes. That can also happen.
Okay, thank you.
Hello, thanks for the talk.
Yeah.
I have a question especially in data centers, we see the trend that most of the network function is moving into smart NIC. So even NVIDIA, AMD, Intel, they are coming up with smart NICs, and almost all of the network functionality has been handled by them, and they are freeing up the CPU to run user programs.
Yeah.
So how do you see this evolution going ahead?
Yeah.
Will the kernel evolve, or this is a permanency that we will see in the future?
So that's a good question. So there's actually in this set of things, right, there's actually another thing which I didn't talk about. So you're moving it into the kernel, or you're doing kernel bypass. The third option is you're actually pushing it into smarter hardware. So you're having programmable hardware, smart NICs with attached FPGAs or programmable switches, all of which are kind of absorbing some of the packet processing, so that everything, your kernel, user space, everything is freed up. So that is also a trend. So I think these are complementary. I don't necessarily see one as overriding the other, because this hardware is expensive, right? And you are in some sense locked into a certain hardware. Things like, suppose you want to migrate your VM from one machine to the other. If you're locked into a smart NIC, you are basically limited in your VM migration capabilities. So there are pros and cons to doing things in hardware. It is obviously more efficient, programmable hardware, versus doing it in the kernel or kernel bypass. So the way I see it is both of these will go hand in hand, right? And both are valid ways to make your applications perform better. Okay.
Yeah. So with that, we'll end the session.
Okay. Thank you all. Any more questions? I'll be happy to talk to you during the tea break. Thank you.
Yeah, I'd like to invite Professor Shivaram to provide a token of appreciation to Professor Maithili. So we move to the next segment of our event, which is student talks. We'll be having three talks in this particular session. Two will be from students and one will be from the GISC division of our college. I'd like to invite Anshuman Dhulia here. Anshuman is a PhD student, and today he'll be talking about synergistic program analyzer, which is a project he has been working on. Over to Anshuman.
Hello.